Okay, our introduction says that a vendor at the concert was selling toasted almonds, which were $3 a pound, and an extra $2 if you chose specialty wrapping. Abby, one of the groupies, wants to buy her mom 2 pounds, specially wrapped, for her mother's birthday. She claims it's going to be $10, but Charles, another groupie, says it's only going to be $8. So we have to get in between them and figure out who is right, and we have to explain. So we should be getting pretty good at realizing that we can write an equation for this. We have two different variables that we're looking at, pounds of almonds, as well as the total cost. Okay, I'm going to represent this as P, this as C. I know that the cost depends on pounds, so here's my independent variable, and here's my dependent variable. Those are just nice review from last section. Now I'm going to go ahead and write this equation. I know it's $3 per pound plus the extra $2 for the specialty wrapping is going to be my total cost. I also know that she wants 2 pounds. So the cost of this, or I'm sorry, not the cost, the pounds of this are 2, which means I'm going to take that 2 and plug it in over here. So I know that the cost is going to equal $8. Who was right? Charles. Charles is right. I'm not going to explain because my algebra explains for it. My equation explains it in algebra terms. The reason why I have this problem in here is because we're dealing with functions in this section. Okay, this is considered a function, and the reason being is that no matter how many times I go and ask for 2 pounds of toasted almonds specially wrapped, it's always going to be $8. Okay, no matter how many times I put 2 into my function machine, 8 is always going to be spit out. All right, there is no way that I'm going to get another value for putting that 2 in there. Okay, that value is not going to repeat for anything else. Okay, that also means that if I go back here and ask for 2 pounds tomorrow and they tell me that it is $10, I know something's up. Okay, so this is a function because this x value is never going to repeat. There is going to be no other value for those 2 pounds of almonds except for those $8. All right, another thing. Well, I think I'm going to talk about that later. Yep, so that's as far as I'm going to go with that this is a function because no matter how many times I buy 2 pounds of almonds, it's always going to be the same value. Now we're supposed to create a graph to represent the situation. I'm glad I labeled these independent and dependent because I know that my independent is always my x value, my dependent is always my y value. I could set up an equation here or a table, but I'm actually going to use ordered pairs because I know that that's what I'm going to plot over here. If I just bought 1 pound of almonds, I know it's going to cost me $5. If I bought 2 pounds of almonds, I know that's going to be $8. 3 pounds, if I plugged it in there, is going to be $11. And I'm just going to go up to 4 pounds. That's going to cost me $14, right? Let me do some math here. Probably would be handy, huh? All right. And I'm just going to go up to 4 because I need to just write a quick little graph here. Okay, pounds. Setting up this equation again, I'm going to skip tick marks. There is exactly 14 here, so I'm just going to go 1 and 2. So I understand that each one of those is 1 tick mark. I don't have to go all the way up there as long as I can effectively graph it on here. So 1 is 2, 4, 5. That represents 1 pound is $5. 2, 2, 4, 6, 8. 3, 8, 9, 10, 11. And 4, 11, 12, 13, 14. All right. Noticing a couple of things. Look at our equation. I have 2 variables. They both are to the power of 1. I know that because of that, I'm going to have what's called a linear equation. These are going up at a constant rate. Okay, one thing that I know about it. Another thing, it asks, can I connect the dots? So what that means is, are there values in between these dots that I could actually have? Well, let's answer that question. We're dealing with pounds. This value right here is 1.5 pounds. Can I buy 1.5 pounds of almonds? Sure I can. So can I connect these dots? Yep. So I am actually going to do that. Okay, but I do have to answer that question. Why was I able to connect those dots? So can I connect them? Yes, we decided. And I'm going to say that you can have part of a pound of olives. Pound. Why does that sound weird? Because we're not dealing with olives, we're dealing with almonds. Part of a pound of almonds. Okay, this is what's called a continuous function because I can connect the dots. Moving on to this next one. Specialty shirts are on sale again. This time each shirt is $10 with the cost of $20 per order to put names on the back. We're supposed to write an equation that represents this situation. Again, two things that we're dealing with are shirts and total cost. S and C. Cost still depends on those shirts. So review a vocab from last time. There's our independent and our dependent. They do want us to write an equation on this. So looks like it's $10 per shirt plus $20 for the order is going to give me the cost. Then we're supposed to find out how much it will cost if all 7 members bought a shirt. So they're telling us that we want 7 members. I'm sorry, why do I put C? We want the shirts to equal 7. So I'm going to plug a 7 in there, and that's going to give me my cost. So $70 for the shirts plus $20 for the processing fee gives me a cost of $90. Okay, so I circle this and I forget about this, and then I come back in a couple days and the only thing that I had was my answer. I didn't have any of my work. And I was trying to explain how I got that answer to them. And I couldn't do that because I didn't have my work. I didn't know what I actually put into my machine. So what I'm going to show you is what's called function notation, which is what we're going to use in this section. And another way to think about this, we have our little function machine that's telling us to take a number, we're going to multiply it by 10, and we're going to add 20 to it, and it's going to spit out another number. And we're supposed to put those two numbers together, kind of like up here. Except when we were putting numbers in our machine, we were daydreaming. Okay, so we put a 6 in there, we spit out a number. We put the 7 in there, it spit out the 90, but we forgot what number that went in. So we don't know what they're tied to. And if you just had this circled that C equals $90, that doesn't tell us how many shirts that is. And that's what function notation does. This is what I really like about it. We're going to say how we write this is C of 7 equals $90. So instead of just putting C, we're going to do what's called C of 7, which is function notation. Because what this means is 7 shirts cost $90. So now we actually have a sentence that deals with both the shirts and the cost. Okay, function notation I love because it does show the relationship between the input, which was 7, and the output, which was 90. All right, we are supposed to create a graph that represents the situation. Again, we're dealing with shirts down here, and we're dealing with cost. Let's just go ahead and do 4 and cost. We can go by tens. 10, 20, 30, 40, 50, 60. So let's go by tens like this. Again, I'm going to write these in ordered pairs. That if I bought one shirt, it would cost me 30 bucks. Okay. I could function notation, C of 1 equals 30 to be fancy, but I'm not going to. I just want to show you what that would look like. One shirt costs $30. 2 actually doesn't cost 50. I need to slow down and do the math on this. If I put 2 in here, it costs 40 because it's just always going to cost me $10 more if I increase by one shirt. So 1 is 30, 2 is 40, 3, 50, and 4, 60. All right, so there we go. Again, knowing that I should have a linear equation there because I'm dealing with two variables that have a power of 1. Let's go ahead and look at that question again. Can we connect these dots? Why or why not? Well, let's look at what we're dealing with, shirts. This value right here means that we have 1.5 shirts. Can I buy half a shirt? It's not considered a tank top, so no, we can't. So question, can we connect these dots? No. And we're going to say cannot have half or part of a shirt. I'm not going to put half, I'm going to say part. Cannot have part of a shirt. This is what's called a discrete function because I cannot connect the dots. I can just have the dots. Some students get line crazy that they want to connect dots all the time. This is a great section to have them slow down and understand why did I make this graph and what does it represent. So many different concepts that we're going to talk about in this section. We're going to talk about functions and go over that a little bit more. We're going to talk about continuous and discrete functions. And we're going to talk about function notation. So go ahead and get your notes out for this section. Okay, objectives of this section are to represent or identify a function in a table or graph as having exactly one output for each input, and to evaluate linear and quadratic functions for values in their domain when represented using function notation. Okay, going over a function. There's many different definitions of this, so they have theirs and I put mine there as well. A function is a relationship between input and output. In a function, there is exactly one output for each input, which means is that the x value cannot repeat. So there's many different ways to look at relations, which means that there's many different ways to test a function. So looking at a mapping diagram, again, I put a couple other little rules here that when we're looking at a mapping diagram, only one arrow can come from each one of the domain. Because if we had 2 arrows, that means that we have a repeating input and we can't have that. Ranges can repeat. So if I had a 5 down here and that arrow was over here at 2, that's okay. It's the domain that we care about. And we're going to look at graphs a little bit later. So example 1, they just have to pass all those tests. Determine whether each relation is a function and explain. Well, here's our mapping diagram. The rule was that we can only have one arrow from each of the domain. Did it pass the test? Yes. Is this a function? Yes. And we are going to say why, because only one domain value is paired with the range value. Okay, domain didn't repeat. Might be a better way to explain that. Okay, looking at B, this is a table. I like tables because, again, what we care about is that domain. So we're going to look at this domain and make sure that these numbers do not repeat. I have a 1, 3, 5, 1. Whoops, I have a problem because my domain did repeat right there. So is this a function? No. Why not? X values repeated. Input values repeated. Independent variable value repeated. All of those are synonymous. So I'm going to say domain value repeated. Okay, that's the biggest thing. X values cannot repeat. So go ahead and look at Guided Practice 1, which deals with ordered pairs, which again, we can kind of, if you want to, set that up as a table and test it from there. Okay, going to the test, we're looking at just that X value. I had 2, 3, 3, there's a problem right there, and then back to 2, which is a problem. So this definitely isn't a function because the X values did repeat. So functions, X values cannot repeat. So we go straight for that domain or straight for that X value. Next up, we're looking at those discrete and continuous functions with could we connect the dots or not. So a discrete function consists of points that are not connected. Those were our t-shirts. We can't have part of a t-shirt. Continuous function, functions graphed with a line or a smooth curve. We could have part of a pound of almonds, so we could connect those dots. So let's look at ice sculpting. At an ice sculpting competition, each sculpture's height was measured to make sure that it was within the regulated height range of 0 to 6 feet. The measurements were as follows. Team 1's info is there, Team 2, Team 3, Team 4, and Team 5. First thing they want us to do is make a table of values showing that relationship between the ice sculpting team and the height of their sculpture. So again, we want to see this relationship between Team 1 of having 4 feet, Team 2 of 4.5, and so on. 3 as 3.2. Remember, these are all relations, that these numbers are related to each other. Okay, now we're supposed to determine the domain and range of the function, and this is just a review of what we did last section. We know that domain is a set of numbers 1, 2, 3, 4, and 5. And that's what those little brackets mean, the set of numbers. Our range are the y values, the set of numbers 4, 4.5, and so on. Okay, we're supposed to write that data as a set of ordered pairs. Best place to look for with that is this table that we know that Team 1 is 4 feet, Team 2 is 4.5, and so on. Realizing that this is the third way that we have represented, I can't talk and write at the same time. This is the third way that we have represented the same type of information. Getting used to that, especially when we're dealing with graphs. Because look at this, now we're supposed to graph the data, the fourth way that we're going to look at this information. So Team 1, 4 feet, Team 2, 4.5, we're going to have to guesstimate a little bit there. 3, 3 and 2/10, which is even a little bit more. 4, don't select the page, please. Where am I at? 4 and 5. Okay, big question here. State whether the function is discrete or continuous and then explain your reasoning. Again, I always like to go straight for that x value and look at halfway between and figure out what that is. That is saying that I have 1.5 teams. Can I have team 1.5? No, I can't. So that would be discrete because discrete do not connect. So I'm going to say that they are discrete. Explain my reasoning. I'm going to say cannot have part of a team. Okay, go for that x value and try to interpret what that x value is representing. Okay, moving on. Guided practice 2 does have a lot of different concepts put together, so do make sure that you understand all 4 of those sections. Okay, many different concepts. Domain is that x value, range is the y. Taking that, writing it as a set of ordered pairs, using those set of ordered pairs and graphing them. Stating whether this is discrete or continuous. So looking between here, 1.5 quarts of seed. Can I have that? Yes, I can. Okay, so I'm going to say that this is continuous, that I can have part of a quart. Alrighty, moving right along. Going back to the whole function thing. Sometimes we can see the x value not repeating. Other times, if we're looking at a graph, we can do what's called the vertical line test. And it says you can use the vertical line test to see if a graph represents a function. If a vertical line intersects the graph more than once, then the graph is not a function. Otherwise, the relation is a function. So what I do is I call this kind of the raindrop test, that if I take a raindrop, if it rains, that raindrop can only hit the graph one time. If it only hits it once, it's a function. So that's why it's a function. It hits one time. Raindrop on this one hit it once and twice. We have a problem, so that's the reason why this is not a function. The third one's a really weird looking guy, but this open circle means that that is not a value up here. but it is here. So if we combine these two, we should be okay. That's why it's a function. Notice how we're talking about relations and functions. Again, recall that an equation is a representation of a relation. All three of these are relations. These ordered pairs are related to each other. It just happens to be that it's not a function. This is both a relation and a function. Relation and a function, relation and not a function. Alrighty, let's go ahead and look at that vertical line test. We're supposed to look at these equations and determine whether they're a function or not. We haven't really gotten into graphing these, but this is a nice little precursor for what we're going to do next section. I'm going to plug in some x values and figure out what y values coincide with them. I like to use numbers like 0, 1, and 2. Those are nice little numbers. So if I plug a 0 in for x, what am I going to get out for y? I'm going to get out an 8. If I plugged a 1 in there, that's -3. I would have to add that over. So I end up with 11. If I plugged a 2 in there, that's -6. If I added it over there, that's going to be 14. So a lot of times we use 3 values just to make sure that each one of them is correct. And then I'm going to go ahead and plot those, 0, 8, 111, and it looks like I'm off the charts on this one of 2 and 14. Okay, looks like this is a pretty linear equation, and it should be, because we're dealing with those 2 variables and they're both the power of 1. Now let's go ahead and do our vertical line test. Looks like this is going to pass. So is this a function? Yes. Yes, it is. All right, this guided practice, of course, this first one is a little bit tricky because notice up here we did compare our x's and y's. Down here I don't see a y. So what I'm going to do is I'm going to go ahead and solve this for x by dividing that 4 over, and I realize that x equals 2. Now what this means is that x is always going to equal 2. So if I set up my equation, I can't choose my x values that I'm going to put into my little function machine. It's always going to be 2. So when y is 0, x is 2. When y is 1, x is 2. And so on. If I plotted this 2, 0, 2, 1, 2, 2. Look at this. This is definitely not a function because there's no way this can pass a vertical line test since it is a vertical line. So I am going to say big fat no on that one. All right, go ahead and try 3B. Put a couple values in for x, figure out what y value coincides with it, graph it, vertical line test, and either write down yes or no. Okay, we are definitely going to get more in depth with graphing equations in this next section. So if that is a little bit confusing to you, really what we need to know is, again, that vertical line test. Does it hit more than once? Nope. So we're good to go. This is a function because it did pass the vertical line test. This is a nice little representation, again, to see all of the many different ways that we can represent a function. And now we're on to that function notation. Again, where we couldn't remember how many shirts we bought to equal 70, so we had to rewrite it in function notation to understand it. So it says that equations that are functions can be written in that function notation. For example, consider, a lot of times we like to use x as our independent, y as our dependent. The function notation gets rid of y, and they write f of x. I always tell the kids, this is the fancy way of saying y. That's all it is. They're just very fancy here. Okay, we're upper class now because we use function notation. I'm going to read what they wrote. In a function, x represents the elements of the domain, and f of x represents the elements of the range, or the y values. And it shows us, suppose we want to find that value of the range that corresponds to 5. We write that as f of 5. Okay, the value f of 5 is found by substituting the 5 in for the x. So that's what we're going to do here. So in order to do this, again, this f of 2, what this means is substitute 2 in for x. So instead of saying evaluate when x equals 2, they're just now writing f of 2. And this is how we do it. We say f of 2 equals negative 4 times 2 plus 7. Okay, this is just our way of saying y. So I'm going to keep bringing that down. I have negative 8 plus 7. Going to keep bringing that down, and I get negative 1. So what this is saying, this is actually our final answer. This is saying that when x is 2, y is negative 1. Okay, in math talk, that is what that means. And I'm going to move that. Whoops, that did not work. So I have room for this. No, I think I have room for this next problem. Okay, this next problem is a little bit different because we have that plus 1 out there. So what we're going to do is we are going to, first off, holy cow, I'm sorry, let me get this cleaned up. Okay, first thing that we're going to do is plug in negative 3 in for the value of x, and then we're going to take our answer and we're going to add 1 to it. We're not going to use our fancy equation here because it doesn't really work for this because we have that plus 1. So they are saying sub negative 3 in for x. I'm not going to deal with this. I'm going to say negative 4 times the negative 3 plus 7. Then I have to add in this plus 1. So here we go. Negative 4 times negative 3 is a positive 12 plus 7. So there's my actual function. Then they said go ahead and add 1 to that. Okay, we have 19 plus 1. The value of this is 20. Getting used to what this means, just subbing negative 3 in for x. All right, go ahead and try this guided practice, understanding what their talk means and what we're supposed to do with it. Okay, 4a and 4c are pretty straightforward because, again, they're saying plug a 1 in for x and solve. So f of 1 equals negative 1 is our answer, that when x is 1, y is negative 1. When x is negative 2, y is negative 7. B and D are a little bit different. It said that we were supposed to take 6 and subtract the function when f was 5. So we had to go ahead and plug that in there, have 10 minus 3, keep bringing that down all the way to negative 1. Again, read the problem, say it as a sentence. What am I supposed to do? I'm supposed to take 6 and subtract whatever the answer of f of 5 is. This one's even weirder because we were supposed to plug a negative 1 in for the function, figure out what that happens to be. So that happened to be a negative 5 as a value. Then plug 2 into the function, figure out what that is, which was a 1. Combine those two together, and what do you got? A negative 4. So read the problem, actually say it in your mind as a question, and figure out what it is as an answer. So all of these problems, we use function notation with linear equations. If we had to graph this, we knew that it would be a line because our x value is only to the power of 1. Looking at this next problem, we're doing the exact same thing as what we just did, except now these are called nonlinear. If we graph this, we couldn't use a ruler. It would have a curve to it. Okay, we're going to get to nonlinear functions way down the road, but understanding that quickly we can see, oh, this is not going to be a line because we have a power of 2. But we're still doing the same concept here. Even though we look at an h right now and a t, maybe we're dealing with height and time, we're still doing the same thing because this is saying h of 4. Plug a 4 in for our values of t. So h of 4 equals a negative 16. Every time I see a t, I'm going to put a really big parenthesis there, and I'm going to fill in the blanks with a 4 because that's what it told me to do. So h of 4, I'm going to put a 4 in each one of those, And I'm going to make sure that that squared button goes there. And again, this is when we bring out that calculator and plug it in exactly as it states. Okay, remember we don't do anything with that h of 4. That is just our label. That's our little function machine 2.0. So I'm going to plug it in like we did a while ago with our order of operations. And I should get 18. So again, if we plug the value of 4 into our machine, 18 will be our output. Okay, of course we have to have this really weird thing right here where we have quite a few things going on. This is saying 2 times h of g. So this is saying that we are going to plug a g in every time we see a t. Weird stuff. So I know I'm plugging something in every time I see a t. So that means I'm going to put big parentheses anytime I see that t. And then I'm just going to do what I'm told. Okay, it tells me that I'm supposed to plug in a g there. Okay. Can I put that into a calculator? No, that's dealing with a variable. So I know that this is negative 16g squared plus 68g plus 2. What did I do? All I did was I changed my t's to g's. Also says that 2 is out front, so now I'm supposed to multiply this whole thing by 2. So final answer, I have negative 32g squared plus 136g plus 2. Again, what am I supposed to do? Whatever's in that parenthesis, they're saying I'm supposed to plug in for all of the values of that independent variable. I'm going to go ahead and do that, and I'm going to get an answer like this. All right, last guided practice. Go ahead and give it a try. Okay, 5A and 5C, pretty straightforward, taking that t out, plugging in either a 4 or a negative 5. 5B is kind of weird because it says f of t. This is saying plug a t in for all of our independent values that were already t. So I'm just taking the function in itself. It told me to multiply it by 3 and then add a 2. I couldn't technically combine those two because they're not like terms, so that would be your final answer for 5B. 5D says take the function, plug a negative 3 in there, get that answer of negative 54, then subtract the same function of plugging a 1 in, which is a 2, we end up with negative 56. So what is it asking me to do? And then go ahead and do it. Many different concepts, of course, in this section, but I think we can handle the assignment for this section.